Okay, differentiability. A function is differentiable if the left-hand derivative equals the right-hand derivative. All right, so couple of things here. First, if a function is differentiable, all right, if we can establish that a function is differentiable, if we could establish that the left-hand derivative equals the right-hand derivative, then the function is automatically continuous. All right, you don't have to test for continuity. You don't have to go through the three conditions of continuity. If a function is differentiable, if you can establish that the left-hand derivative equals the right-hand derivative, then the function is automatically continuous. All right. However, if a function's continuous, it doesn't necessarily mean that it's differentiable. A great example of this is y equals the absolute value of x, and we'll see that the function is going to be continuous at x equals 0 here, right? This is the point 0, 0. But it's not differentiable because the left-hand limit as we come in from the left, the slope as we come in from the left would be -1, and the slope as we come in from the right is +1. So that function is not going to be differentiable, but it is continuous. Okay, so if a function's continuous, it doesn't necessarily mean that it's differentiable. It might be, it might not be. All right, so when is a function not differentiable? Well, when you have a corner. All right, I think I just kind of showed you that. At a corner, the left-hand derivative is not going to equal a right-hand derivative. At a cusp, do you know what a cusp is? A cusp is kind of like a point that is formed from a couple of different curves. I kind of call it a curved corner. A vertical tangent. All right, this is a little tricky, but a vertical tangent is something like this, where the function's kind of cruising along and then all of a sudden it comes up, and when you're looking to find the tangent at this point, it actually is a vertical tangent, and you try to find the slope of that line, and it's obviously undefined because the slope of vertical lines are undefined. Okay, so if your tangent line is vertical, then the slope of that tangent line is undefined, and if the slope is undefined, then it's not going to be differentiable because the derivative is a slope, so you're not going to be able to find the slope. And the fourth place is at a discontinuity. So if the function isn't continuous because of a hole, it's not continuous because of a jump or because of a vertical asymptote, right? That's like the tangent graph, right? Then the function's also not going to be continuous, right? So I usually think of problems with, the function's not going to be continuous or differentiable for a vertical asymptote. Right, so back to differentiability. I think of 6 problems that differentiability has. A corner is one problem. If there's a corner, it's not going to be differentiable. If there's a cusp, it's not going to be differentiable. If there is a vertical tangent, it's not going to be differentiable. If there is a hole, a jump, or a vertical asymptote, the function will not be differentiable. Okay, so there's 6 different problems for differentiability, where if you think back to continuity, you only kind of had 3 problems for continuity. All right, so for a function to be differentiable, it's a little bit more tougher than for a function just to be continuous. All right, so let's go through some examples here. Determine if this function is differentiable at x equals 0. Okay, so what we need to determine is the slope as we come in from the left and the slope as we come in from the right. So this is the left side equation, right? So if we take the derivative of this left side equation, the derivative would be 0 minus 2 minus 2x, right? And we need to evaluate that derivative at x equals 0. Okay, so if we evaluate this derivative at x equals 0, because we're approaching, right, x equals 0. That's why I'm evaluating it at x equals 0. So we get -2, right? So the slope coming in from the left is -2. All right, what about from the right? All right, so if I take the derivative coming in from the right, that derivative is going to be 2, right? If I evaluate that at x equals 0, I still have 2. You know how I'm getting a derivative of 2, right? I'm just doing the power rule. And you know how I got This derivative coming in from the left, same thing, I'm doing the power rule, right? The derivative of a constant is 0. The derivative of negative 2x is negative 2. The derivative of negative x squared is negative 2x. All right, so what's my left-hand derivative? Remember, in order for a function to be differentiable, what's the definition? The left-hand derivative needs to equal the right-hand derivative. All right, so at x equals 0, what's my left-hand derivative? Negative 2. At x equals 0, what's my right-hand derivative? Positive 2. That's not going to work. All right, it's not differentiable because the left-hand derivative does not equal the right-hand derivative. All right. All right. If you really wanted to explore that further, you could sketch the graph. You could make a quick XY sketch of the graph. So what's happening at negative 1 at 0 as we come in from the left. So if I take these values and plug it in here, I get 2 plus 2 is 4. Minus 1 is 3. I think it's 3. Don't quote me on that because I'm doing it quickly. And then at 0, it's going to be 2, but that's going to be an open circle, right? So let me just come up here. And so we've got something like this. Right, so it's a parabola, so it looks something like this. So as we come in from the left, our slope here is negative 2, right? We knew that from that. That kind of makes sense. And then what about as we come in from the right? Let's plug in a 0 and 1. All right, so we're plugging 0 in here. We get 2. When we plug 1 in, we get 4. All right, so it's at the point 0, 2, so we could fill that point in so it's continuous. And then the point 1, 4 is up here. But again, the slope coming in from the right is a positive 2. All right, so this looks like a cusp to me, right? This is a cusp at x equals 0, so it's not going to be differentiable. All right, so that's a lot of extra stuff that we didn't need to do, but kind of gives you a real good idea of, is it continuous, is it differentiable, and if it's not differentiable because the left-hand derivative doesn't equal the right-hand derivative, you know, what's a picture of that look like? Well, now you've got the picture. All right, how about this second example? Determine if this is differentiable at x equals 1. Okay, so let's take the derivative of this piece. The derivative of the left side coming in is going to be 2x. When we evaluate that at x equals 1, we get 2. So the derivative coming in from the left is 2. How about from the right? What's this derivative? Well, that's pretty easy, right? That derivative is 2. When we evaluate that at x equals 1, there is no 1 to plug in, so we get 2. So yes, the left-hand derivative equals the right-hand derivative, so yes, this is going to be differentiable. All right. Okay. What else? What else could we go through with you? Here's a great example. Example 3. If this function is differentiable, find a and b. Ooh, what a great question. So if the function is differentiable, let's think about this for a second. All right, then the left-hand derivative is going to equal the right-hand derivative. So we'll take this left piece and we'll take the derivative of it. What's the derivative of 3ax squared? 6ax, right? Remember, a is a number. We don't know what that is yet, so we'll just kind of leave it down there and pretend it's a number. What's the derivative of 2bx? 2b, right? There's a constant in front of that x, so it's 2b. And what's the derivative of plus 1? 0. All right. Okay, how about on the right side? What's the derivative of this equation? Well, it's 4ax to the third minus 8bx minus 3, all right? So they are telling me that this function is differentiable. So the left-hand derivative has to equal the right-hand derivative, and it's differentiable at x equals 1, right? So if I plug x equals 1 in for this, let's see what I would get. 6a plus 2b equals 4a minus 8b minus 3, all right? Now I could clean that up a little bit. So I could subtract 4a from both sides. I could add 8b to both sides. And we'll just leave the negative 3 over there. But there's nothing really else that I can do with this equation. And I'm in trouble because I have two variables. I need to solve for both variables. And I've only got one equation. That doesn't work in math. If you need to solve for two variables, guess what you need? Two equations. So how could we come up with a second equation? Well, do you remember that I told you if a function is differentiable, it automatically has to be continuous. All right, so that's the key to this problem. Since they told us that this is differentiable, then it's also going to have to be continuous. All right, so this function is going to be continuous at x equals 1. If it's continuous at x equals 1, what does that mean? Well, it means that this y value is going to equal this y value at x equals 1. All right, so let's set these two y values equal to each other. And we're going to set them equal to each other at x equals 1. All right, and these guys are going to be equal to each other at x equals 1. So let's plug 1 in for x. We get 3a plus 2b plus 1 equals a minus 4b minus 3, right? All right, so let's clean this up by subtracting a from both sides, adding 4b to both sides, and why don't we subtract 1 from both sides, just so that this can kind of look like that, right? So now we have our two equations. Now we can solve them simultaneously. We could put one equation on top of the other, and we'll be all set. Right, you could solve this using substitution. There's a number of different ways you could do this, but what I'm going to do is multiply this entire equation by a negative 1. All right, so if I do that, both sides of the equation, I'm allowed to do that, right? Whatever I do to one side of the equation, as long as I do to the other side, that is legal. All right, and this top equation here, I'm just going to leave as is. I'm not going to touch that. And the reason why I'm not going to touch that is because now when I add these two equations together, these are going to cancel. And I have 4b equals 7. So b equals 7/4. Not pretty, but that's the answer, right? All right, and that's for b. I also needed a, so now I can go back to any of these equations, and I could just substitute in 7/4 for b. So let's see here. If I take 2a plus 6b equals -4, and I plug 7/4 in for b, I can get my value for a. So let's see here. This is going to be 2 and 3, so we have 21 over 2 equals a -4. So 2a equals, let's do this on the calculator here to make my life easy. I know I probably shouldn't do this, but -4 minus 10.5, whoops, is going to be a -14.5 divided by 2 should be a -7.25. Is that right? I hope that's right. All right, so hopefully that is correct. Let me just check my work there very quickly. So, yep, 21 over 2 is 10.5, right? Yep, and then if I subtract that, so -4 minus 10.5 is that divided by 2, -7.25. Okay, so there you go. So I've got my A value and I've got my B value. All right. All right, so that was a good one. All right, let's give one more shot. If this function is differentiable, find the values of a and b. So now you probably know how to do it. If the function is differentiable, that means that the left-hand derivative is going to equal the right-hand derivative. So let's take the derivatives of these two equations. The derivative of ax plus 6 is just a. The derivative of bx squared plus 7 is 2bx. And they have to be differentiable at x equals 1 because that's where they meet, right? All right, so if I plug that in, I get a equals 2b. We'll just leave it like that for now. And then if the function's differentiable, it also has to be continuous, which means that the y values need to equal each other at x equals 1. So we've got a plus 6 equals b plus 7. All right. And we could simplify that a little bit if you wanted to. A equals b plus 1, subtracting 6 from both sides. And now what I can do is I could use substitution. I could take 2b and substitute it in for a. All right, so that'll allow me to get b equals 1. And once I get b equals 1, I can go back to any of the other equations and figure out that a has to be 1 plus 1 or 2. All right, so pretty easy once you understand that when a function's differentiable, it's also got to be continuous. All right, I hope that helped.